So today we're talking about Hamiltonian formalism. And as I mentioned last time, the Hamiltonian formalism is the evolution of the Lagrangian formalism, where Hamilton, so this is the Lagrangian, it depends on the coordinate q, it depends on the time derivative of the coordinate q, and with it, you're getting this momentum by taking the partial derivative with respect to the velocity of q. You get this momentum. So what Hamilton was trying to do was get something that wasn't coordinate and coordinates time derivative, but rather two things that we know about well enough: the general coordinate and the generalized momentum. So if we're looking at this from the point of view of a picture, let's see. We want to have an illustration of what this means. Before, let me make this picture here be about configuration space. So this is your Q and Q dot. And we would have a starting point here. And then maybe in configuration space, it looked like this. And that's the flow, the direction that this system is taking over time. Now, in the Hamiltonian formalism, we're thinking about, let me rewrite this, phase space. So this is not configuration space, because now we're thinking about Q and Q. So this is a bit different. Remember, in configuration space, we were thinking that there's a point Qi. So in configuration space, we're in Qi, and it's about the Q's only. And you have an n-dimensional Qi defines the n-dimensional space of the system. So this is our configuration space. The time evolution is dictated by that arrow. And in phase space, we're actually thinking about this Qi and Ei. So you have a set of Qs, you have a set of Ps, as opposed to just having the Qs. And the state of the system is defined here by this flow right here, by this direction, a starting point. Here we could say that we have a starting point, and then it's just gonna follow like that. This pair of coordinates is your 2n dimensions. And something that is important is that the state of the system here is defined by the Qi's. The state of the system here is defined by the Qi's and the Pi's. So with these two guys, I know the future of the system. Here, I just needed this guy. Now, the most important thing, though, is that in this two-dimensional space, that we 2n-dimensional space that we have here, This point tells us exactly the time evolution of the system. So from an initial point in phase space, you determine the future evolution of the system. And that means that paths don't cross in phase space where we saw that paths cross in configuration space. So that's the main distinction. Another aspect that is very important is the flow of phase space. So this is the flow of the phase space. You take a portion of flow space and you can see where it's going to get mapped into the future. You don't do that with configuration space because the path is not determined by the points Q by themselves. It's determined by Q and Q dot. Okay? Questions about this? Yep. All right, so this is the most important concept difference between the two. So let's go back to examples. And back to our favorite, the pendulum. So let's see. Well, we have the pendulum, just a simple pendulum, right? Michelle? Yeah. What is the coordinate that is important in the pendulum? Theta. Theta, right? So if we look at theta for the pendulum, configuration space is theta, and this theta can go from negative pi to pi, right? Like this. And that means that's configuration space. So if you look at it, this is one configuration space. And that's all you have to worry about. So phase space, though, is not the same thing. Anybody know why? The momentum is not bound here. Because you have those two things, momentum and theta, right? In phase space, you would be working with theta and the momentum theta. So now, if we look at this, geometry-wise, this is S1 is the group that this belongs to. It's just a one-dimensional parameter space, right? But phase space is not. Phase space is actually R cross S1. This R is your momentum. So looking at it, so this is the phase space is now this two-dimensional thing. Looking at it, this is a circle, right? And like you said, this momentum is not bound. So instead of having a circle, you have a cylinder. Awesome. Does that make sense? So how do we how can we picture this in our heads, right? So let me draw this two-dimensional system. This is one of the axes. So this is the other axis. So this is my theta axis. This is my p theta axis. And now, well, I'm gonna have this very important point right here, and this very important point right here. This corresponds to theta is equal to pi. This one corresponds to theta is equal to negative pi. This one corresponds to theta is equal to 0, right? Now, what we have is then that what's going to happen if my momentum is 0 and theta is 0? Sorry?
Is it at rest?
At rest, right? So that's one point of motion. Did you see that one? It's just tiny right there, tiny little dot, right? Now, we could look at momentum 0, but theta not being 0, right? So if we start here, right? And we know that that one is actually going to go in that direction, and this is supposed to be a circle, right? So it has this kind of motion. So that's your small angle. You put it at this angle, you let it, you're gonna let it go from there, and it can go like this. So that's represented by this. And we have bigger ones. If you put a bigger angle, it's gonna go like this. Okay. And if I have even bigger angle, it's gonna look like this. Right? Question so far? That means if I put it up like this, momentum 0, let it go, and it's gonna go all the way around. In this up one right here, you could go all the way down, and then it gets to this point. And then if it starts at 0, it's at 0 momentum there, right? Because it's at rest all the way at top, and then it's gonna come back down. So now it's gonna have the opposite. So you guys see how this circle becomes the oscillatory motion. Is that clear? This branch and this branch is the oscillatory motion. This last one that I drew is the one that starts at 0 momentum, but at all the way on the top, and then you go all the way around. All right, questions?
Sir, in this, the pendulum we are considering, is it moving like this? Like we are taking from -pi to pi. So, so is it not just this? Like,
Yeah, right here.
Yeah, that I understood, but it's we are.
All right, so let's look at it. This is really important. Okay?
Yeah.
If you're at 0 momentum here, some angle here, and then you let it go, it's going to go like this, right? So when it's at 0 angle, it's going to have some momentum in that direction. So it's going like that. When here is when it's going in that direction and flowing in that direction. And then it's going to get all the way to this point where it's 0 momentum here at this angle over here. And then it's going to go back down in angle all the way to 0 momentum, all the way to over here. So this direction is the only one that works to do this kind of motion. this path, there's no opposite clockwise. So this is clockwise, right? There's no anti-clockwise. Do we need to sell our Bitcoin? You sure? You have to tell us. I don't want to go poor. That's all my savings. So there's no secondary. So there's this point in phase space, right? This is the important thing. This point in phase space right here tells you the whole motion. This point in phase space tells you the whole motion. So it combines both going that way and this way. So that's the oscillation motion. If you go at zero momentum over here and you let it go, it's gonna go all the way down like this, your pendulum. When it reaches this point, it's going super fast at zero angle. And it's gonna continue with the same momentum until it reaches the top, which is the pi. So you went from negative pi to pi, which is the same point, right?
Yeah, that is the reason why we have defined it as a semi-closed, half-closed.
So it's the same point, but it's going back to itself. And then if it's over here, and now it's going in this direction, it's taking this one. So you could have something that goes like this, and then like that. This one and this one.
We have this full oscillation, but it has a 2 pi angle.
No, it has pi. Negative pi to pi. That's the 2 pi that you want.
I often consider it like this too, right? If the
Yeah, but
pendulum is like
yeah.
that, and maybe it's swinging like this. If not,
Yeah, if it was doing that, then it's this picture. Right? So this is going the whole circle. This could be going from 90 degrees to 90 degrees on the other end. And then this one is the small oscillations. Does that make sense? All right. But we have another quantity, another thing that could happen. And the other one that is interesting is that we can have motion up here. And actually this should have a little bit of a curve. So it should be going like this. Okay? Like this. Like this. So maybe if it's going really fast, it doesn't have a curve, but it should have a little bit of a curve. And this motion is rotating. And in this case, it's rotating anti-clockwise. And we have the ones on the bottom that correspond to this one, and they're supposed to be symmetric, okay? And this one, right? In that direction. And those two is rotating clockwise. So what does that mean? When it's passing at this point right here, the momentum was zero exactly at the top. So it's an oscillate, it's not a stable equilibrium. But this one right here is a higher momentum. So if I put my thing right here, so these are just representative lines. The whole phase space of your pendulum is occupied. You give me I ask you, what are the initial conditions? You point to a position in this plot. And then I tell you the motion of the pendulum with no, nothing else to do. So if you point here, right? That means that you're putting it at negative pi, and its momentum is not zero. So that means that it's doing this kind of motion, right? And it slows down when it's on the top, It's slower here, then it's slower on the bottom. And it just keeps going in that direction. So if I start anywhere here, anywhere above this line right here, this is the line that goes at 0 momentum, I'm gonna have the rotation like that. If I start below this line, I'm gonna have the one that is, which one is clockwise for you guys? Like this? Like this. Okay, so I'm pointing the right way. Make sense? Questions about this? So oscillation back and forth, swinging all the way around. And starting it upright. So yeah, maybe I should do this. Oscillatory motion, it's all the way over here. And this one right here is also oscillatory motion, right? But also this one, just that line, is called the separatrix. Separatrix. It starts upright, falls, and then just makes it back up to upright. So that's the curving phase space of the pendulum. Questions? Anything that's not clear? All right, so if you got that, then now you know the main approach. Yep.
In the first part, small circle,
Mm-hmm.
it goes back and forth. The direction is every direction will be the same.
Right, exactly. You can only flow in this direction.
But it swings like.
All right, so you started here. Momentum is 0. Then let it go. Your angle increases. So it goes from negative, let's say pi over 8 to pi over 8. Your momentum was the largest at 0 theta. So that's going from here to here. And then it's going to stop. So its momentum is 0 at pi over 8. And then at pi over 8, it starts going the other way. So at pi over 8, now the momentum from 0 goes in the opposite direction. So it goes in this direction right here until it passes through 0. And its momentum, which is in this direction, the negative theta direction, is at its maximum. So this point right here is when it's going in that direction. This point is when it's going in that direction.
So the motion above that line and below that line are separate. The circle represents.
So that's your oscillation, exactly. On the top is going to the left, not to your right. On the bottom is going to the left. So you don't have one that points the other way. They're all pointing in this direction because that's all the direction there is. There's no equivalent line because this one, the opposite going back is this one. So there's no line pointing, arrow pointing in the other direction. You only have one.
The direction is absolute. I mean, it never changes. Like, so it's rotating like that. So we can never explain the other way around.
Yeah, you explain it with the bottom part of the graph.
I know. What about see the circle like
This one's?
Anti-clockwise.
All right, so if you're going anti-clockwise,
Yeah.
you're going to go faster and slower, but you're never going to change direction. So that's why this motion is separated from this motion by the separatrix.
So the top one can never be clockwise. That's what I'm
Exactly. Exactly.
bottom one.
Yep. So I guess everything above the 0 plane is anti-clockwise because that's how we define it. And everything on the bottom is clockwise. All right, so that's our thing about pendulums and how to explain them better and why Hamiltonians are better. So now let's go back to what the book says we have to cover. And the next aspect would be the Legendre transformation. So a Legendre transformation is what we use when we want to find a function that on phase space that uniquely determines the evolution of Qi and Pi. So this is not the Qi dots, right? And that function has the same information as the Lagrangian. So there's a trick to do this. It's called the Legendre transformation, a math trick. And what we want to do is have an arbitrary function, fx, so if we take fx, f of x at y, and we want to take the total derivative, is this one plus that one, because those are the two parameters that it has, right? Then we're going to define a new function. This one is going to be g. It's a function of x, y, and u. And it is defined by ux minus f of x, y. So now this one depends on three variables, x, y, and u, whereas f just depended on 2x and y. So the total derivative now becomes derivative of the ux part, the total derivative of the ux, minus the total derivative of the f. So if we do that, we're going to have u dx plus x du minus the partial of f with respect to x dx minus the partial of f with respect to y dy. So at this point, the u has been an independent variable, right? U is another variable. There's x, y, and u. So now what we need to do is suppose that u is a function of xy. And we can do that. And even assume that it is df of dx. So that's what I'm going to choose as a definition for u. Then I can rewrite dg. So if if this becomes df dx, then we see that this is df dx, okay, partial of f with respect to x dx minus partial of f with respect to x dx, and things cancel. Then dg becomes x du minus df dy dy. Salud. So g is a function of u and y. It's not a function of x, u, and y, like we were assuming, right? Because if you look at its total derivative, here's the y, and here's the other coordinate, and you don't have the other one. So this is a new function. And if we want to explicitly write g, what we need to do is just look at this thing and invert it, right? So I know what u is, and u is something related to the partial derivative of f with respect to y, to x. So I can invert the relationship and get x. So u x y is equal to df dx. From here, I can write x as a function of u and y. And then we stick that into the g. So g of x, no, sorry, it's no longer x, y and u, right, is equal to one variable of them, u, times x, that is a function of u and y, minus f, that is a function of x, which is a function of u and y, and y. So that's what the Legendre transform is. The Legendre transform, it takes us from a function f to a function g. So that's just the definition of it. The most important aspect, though, is that both f and g are going to store on themselves the same information of your system, whether it's Lagrangian or Hamiltonian. And there's other transformations. You probably have seen it if you took thermal physics already. Legendre transformation is something you do probably for a few weeks in thermal physics. And the important thing is that you can, if you have G, you can get F. If you have F, you can get G. So how do you recover one from the other? All you have to do is, for instance, if you're working with G, you take their partial derivative with respect to U, evaluate it at Y, and that's going to give you the X, U, Y. And if you have the partial of G with respect to Y, evaluate it at U, because that's my two parameters, right? For G is Y and U. you get the negative partial derivative of f with respect to y. So just as there's this g of u times x minus f, you can also write f, which in this case would be partial of g with respect to u minus g. You can go back and forth between the two. So go back to the original function. So we wanted a picture to understand this. Let's say that this was x. For a fixed y, we're going to have two curves. So let's say that we have this curve going in this direction. And then we're going to have this curve going like this. This curve is u of x. This curve right here is f of x. Okay. For a fixed y value, we have the f of xy here and a ux thing. For each slope of u, the value of gu is the maximal distance between the two values. So in this case, the distance from here to here that's my g of u. That's the maximal distance between the two curves, ux and f of xy, is going to be the value of g of u. So if you want to have more than this picture, if this distance, what it actually means in this case, is this derivative with respect to x of ux minus f of x. So that's my g of u, right? And if I take this derivative and make it equal to 0, I'm going to get that u is equal to df dx. And this is in the language of before, where we're looking that this is the value that maximizes that distance, is one of these trimums, right? So that's the other way you can tell. All right, questions? So this has been just math. Let's get back to dynamics.
In this case, function, this f is on dependent on x, there is no y. So we could just write u equals to dx by dx as an exact differential, right?
No, that's for a y, for a particular y. So this is a function of x and y, and I'm just having a particular y to define it. Yeah, so that's implied at a particular y, there's a u that gets you this value. So this curve is supposed to be in 3 dimensions, and this is just slicing it at a particular y. All right, so hopefully that helps you visualize what a Legendre transform is. So let's go back to Hamilton equations. So if we look at it, Lagrangians are a function of q dots, and maybe time. Sometimes it's not, time is not one of the functions that it is, but you could have it, right? I could give you one on the exam that has a time dependent, right? Maybe your potential depends on time. A potential that turns on and off, on and off. That would be, there's another way to write that on the Lagrangian, right? All right. So we define the Hamiltonian to be the Legendre transformation of the Lagrangian with respect to the QI variable. So this is the variable that we're getting rid of. So if we do that, we get that our Hamiltonian maybe it also depends on time, is equal to, and now you have a summation from I is equal to 1 to however many you have, let's say n, and now you have your pi right here, that q dot, which is the x of before, minus the Lagrangian that goes qi dot, and time. So that means that the q dots are eliminated in favor of the piece. Just like over here, we were eliminating, where is it? Here, we're going from, yeah, so this one right here, right? We're going from x, y to y, u, we eliminated the x. So then that means that we need to figure out a couple of derivatives. So we need to figure out what this one is, but we already knew this one because this one is this right here. And that means that we have pi, which is a function of q. It doesn't have to be the same variable, so let's put it as qj dot, and again time. So now we can invert the relationship that we just put in with the p and the q and the j's, and we know that q dot I is going to be equal to a function q dot I that depends on my qj, the pj, and time. So we have to look at this Hamiltonian and write its variation. Over Hamiltonian, right? And in this case, we would have d of h is going to be, and then we have the first two terms, dpi q I dot plus pi and the total derivative of q I dot minus, and now we have to look at this one, which is the long one. And we have the partial of the Lagrangian with respect to the q's. Then this guy, plus the partial of the Lagrangian with respect to the q dot i's, and then this one. And then let me put this one here, the partial of the Lagrangian with respect to time, derivative of time. All right, questions? That's the same math as before, right? Now just for Lagrangians. And I want to keep going. I can rewrite and this would just be VPI Q dot I minus DL DQI DQI minus DL with respect to time dt. Now, this is the variation of h, but we also know that the variation of h can be defined as, because it has, going back to this equation, right? It depends on the q's, the p's, and the t's. Then therefore I can rewrite it as the partial h with respect to q, derivatives of q's, plus the partial of h with respect to p's, derivatives of p's, plus the partial of h with respect to time, derivative of time. And now we can equate terms. So I'm just repeating the Legendre transform. At this point, I'm repeating Legendre's transform step for step. And now I look at things here and I see that there's things that go together well, right? DTs with DTs, dpi's with dpi's, and I can equate things together. So let me start equating things, but also adding something new. So I'm going to have that PI dot is equal to DH DQI I also have that QI dot is equal to DH d pi and negative partial of the Lagrangian with respect to time is equal to the partial of the Hamiltonian with respect to time. So equating the terms, I get this, and then using Lagrange equation. What do I know from Lagrange equation? That's the one that gives me this point, right? So that's how I go and realize the connection between this term and this term. So these are Hamilton's equations. Instead of having n second order differential equations, we have 2n first order differential equations. So that's the difference between those two. But for solving problems, this is not going to help you, basically because the Hamiltonian and the Lagrangians are almost exactly the same. Seeing things conceptually, it's a big breakthrough. So that's going to be the focus. So first, I'm going to start telling you how to solve things that you didn't with Lagrangians, not to do it in Hamiltonians. But then having some more concepts be transparent with the Hamiltonian. That's the reason we use Hamiltonians. Okay?
Quantum mechanics is much more useful.
In quantum mechanics, you use mostly the Hamiltonian, exactly. But there's also places where the Lagrangian is useful. So yeah, they're both useful.
Because you can really use momentum here.
Sorry?
Is it because we give directly?
Exactly. So that's why it's easier to see how things go in the Hamiltonian motion.
So are we just substituting Lagrangian with Hamiltonian?
Sorry?
From now on, if we are trying to explain the situation, so we